Okay, so we'll finish up Markov chains today. Welcome to our penultimate Stat 110 lecture. So to remind you what we were doing last time, we were talking about reversible, a lot of things about Markov chains, but most importantly, last time we were talking about reversible Markov chains. We did the example, a random walk on an undirected network, right? And there's another important example of reversible Markov chains is birth-death chains, which I think you can read about on the handout. It's worth working through. But I wanted to talk about one kind of generalization while we're still talking about reversible Markov chains. So just to remind you from last time, and then we'll try to extend it a little bit. We were looking at random walk on an undirected graph or undirected network. It looks something like, I'm just going to draw a picture. You have a bunch of nodes, and some of them have edges between them, and there's, they're not one-way arrows, right? They're bidirectional, so you can go, let's say, from 1 to 2, and 2 to 4, and 1 to 4, and 3 to 4, and maybe there's a 5 here that goes to 3, and so on. Whatever we want to draw. We have a picture that looks like this. And if we want, we can add loops, which we didn't worry about last time, but it's no big deal. We could have an edge connecting a node to itself. The only thing we have to be careful about there is there are different conventions for what does this contribute to the degree. So remember, the degree of each node is just the number of edges, and some people like to count the degree in different ways for this. But let's just assume this counts as 1. So in this picture, node 1 has degree 3 because there's this edge to itself and then 2 edges that they're going out. We had a picture that looks like this, and we proved last time that the stationary probability of any node is proportional to its degree, right? That is, if we want the station, we don't have to do any matrix calculations at all. If we want the stationary distribution of the Markov chain, which is just randomly wandering around on this network, all we have to do is list out the vector of all the degrees. This has degree 3, this has degree 2, and just count the number of edges, right? And then normalize that vector so that, multiply by a constant so that it adds up to 1, and then that's the stationary distribution. Okay, we proved that last time using reversibility. So now I wanted to extend that a little bit and say, well, what would actually happen if so we were assuming last time that, like, let's say you're here at state 4, and you see 3 choices. We assume they were all equally likely, right? So 1/3, 1/3, 1/3. So a natural question is, what happens if, certain edges, are more likely for some reason, right? That they're unequal weights. So to handle that, all we need to do is put down some weights. So let's call this W12. I'm just going to put little weights on the edges. This is W11, W14. I'm not going to fill them all in. In general, let's say we have Wij greater than or equal 0. We call that an edge weight. And let's assume that Wij equals 0 if there's no edge there. Right? That just means you can't get from I to j in one step, so we'll just give that weight 0. And then the other ones, it's just any, let's say it's greater than or equal to, well, we can assume it's strictly greater than if there actually is an edge, but it doesn't actually matter as long as we avoid dividing by 0. And then our key assumption is that Wij equals Wji. That's an assumption. Another way to say that is, because we're talking about random walk on an undirected network, and I only wrote one number here, W12. Maybe W12 is 3. It's just some number. But I'm not allowed to write one number that applies going this direction and another number that applies this direction. So it's the same number. Okay, so we may as well just express that as a symmetry condition. Wij equals Wji. And now the way the random walk proceeds is that, so here's our random walk, analogous to what we did before, except we're generalizing it with these weights. All we do is we say, okay, suppose that we're at state 4, and then I see, there's three different possible edges, and each one has its weight. And we look at these three choices, and then we just choose proportional to the weights, right? So if we let all the weights be 1, then we do 1/3, 1/3, 1/3, but maybe W24 is relatively larger, right? It's just proportional. So from state I, go to J with probability proportional to Wij. So that's proportional. Looks like an alpha. That's proportionality symbol to Wij. Okay? So if Wij is 0, then obviously it says we don't go there. So we look at all the available choices and choose with probabilities proportional to the weights we see. Okay, so that's a generalization of the problem, and let's solve this in an analogous way. This is still going to be reversible, and so we want to write down this reversibility equation, SI Qij equals Sj Qji. Okay, let's first write down what's Qij. So if Ij is actually an edge, if it's not an edge, the probability is 0 of going from I to j. If it is an edge, that is that there's an edge there, then by definition, Qij, the transition probability from state I to state j, by definition, it's just the weight divided by the sum of the possible weights, that is the sum of the weights of the possible steps, right? Because it's proportional. So this would be the sum, the denominator would just be the sum of Wik over all k. All right, and we're assuming that the denominator is non-zero because we have to be able to do something, so we don't want all weights 0. All right, so that's the random walk. But notice that then it's true that if we, so in the case without weights, just think of all these Wij's as 1, right? And so then this is just 1 over the degree of I in that case, and in that case, the stationary distribution is proportional to degrees. So the analog of that is that instead of the degree, we're looking at the sum of the weights. That is, from state I, we look at all these weights and we add them up, right? So, okay, so if we do that, notice that if we take the sum of, I'm just going to multiply by this denominator here, right? So I'll take this thing, sum of overall k of Wij. That's the generalization of degree to the weighted case. And if we multiply by Qij, then that just cancels the denominator, which is why I chose that. Okay. That's Wij, but by assumption, Wij equals Wji. So that would be the same thing as if we did it the other way around and did the sum overall k of W, this should be Wik. So we're summing overall, k is a dummy variable, sum overall k Wik, and here we're sum overall k Wjk Qji. That's the reversibility equation. So therefore, the stationary distribution Si, that is the stationary probability of state I, is proportional to this generalized degree, Wik over k. This is proportionality, but if we want to know what it's equal to, we would just divide by the sum of this over all I. So this is completely analogous to what we did last time, but it's good practice. All we did was just multiply both sides by this denominator and use the symmetry, Wij equals Wji. We get the stationary distribution without needing to do any matrices. So this seems like, I don't know if this seems like a small generalization or a large generalization of what we did last time. It's a generalization of what we did last time. Actually, this is completely general reversible Markov chain. So this is actually a complete generalization in the sense that if we have any reversible Markov chain, we can actually interpret it this way. So in a sense, this is the entire theory of reversible Markov chains. Not exactly, because if you have a reversible Markov chain and you know what the SI is, then you're in good shape. But if you don't know that, it may not be obvious to figure out what are the stationary, what is the SI such that SI Qij equals Sj Qji. Okay, but it's a theorem that any reversible Markov chain can be represented in this form. So just to quickly see why that's true. So any reversible chain can be thought of this way. It may not be obvious to figure out how to come up with the Wij's and stuff like that, but at least in principle, it can be written this way. Any reversible chain is of this form. So why is that true? Well, we just need to define the Wij's. So it's pretty obvious what network we should use. We just the nodes are the states, and we put edges, whenever Qij is positive, right? And all we need to do is just say what are the weights. So to do that, let's just say, okay, let Wij equal Si Qij. That's the thing that we wanted, right? But Sij Qij, if it's right now I'm assuming it's reversible, and I want to show that the Markov chain can be viewed in this way. So I'm assuming we already have the S and the Q, and I want to define the weights such that the Markov chain just is this particular random walk. So if we define the weight ij to be Si Qij, but since it's reversible, that's the same thing as Sj Qji. So that will be our Wji. So we will have this condition hold, and all we have to do to check that this works is to show that if we define the weights this way and just do this particular random walk, let's show that it has the transition probabilities that we want, which are the Qij. So in other words, we're assuming we have Qij, that's our Markov chain that we're interested in, and we're assuming that it's reversible, so this holds, and then we're showing that it can be written in this way, right? Well, to do that, at this point, all we have to do is check that this chain, which is random walk on this network with the weights defined this way, has the transition probabilities that we want, right? Which are Qij by definition, okay? So what are the transition probabilities here? Well, I'll just write it as, what's the probability that xn plus 1, if x is, this x process is random walk on this network, xn plus 1 equals j given xn equals I. That's the transition probability that we have. Well, by definition, how do we find the transition probability from I to j? Well, that says, okay, we're at state I, we look around everywhere, what are the available edges, we look at all their weights, and we choose to go to j with probability proportional to Wij. That's the definition of the random walk. So the probability is Wij over the sum of Wik over all k. That was just the definition of how we did the random walk, right? Now, if we plug in what's Wij, Wij is Si Qij, and we divide by the sum of Si Qik, I'm just plugging in how we defined the weights in this way. I'm plugging in the definition. Now let's just simplify this. So this Si in the denominator does not depend on k, so we can take that out of the sum. I'm assuming that the SIs are positive. It's not a very, very interesting chain. If some stationary probabilities are 0, then we should have just restricted the space and not included them anyway. So I'm assuming we're not dividing by 0 here. SIs cancel. So this is just Qij divided by the sum Qik. All right, well, what's the sum of Qik? It's 1. That should be quick, as it says. Why is that 1? Because it's a Markov chain, so you have to go from I to somewhere. So that's 1. So that's just Qij. So in other words, this chain that we constructed has the desired transition probabilities. Okay, so this is the quintessential prototypical example of a reversible Markov chain. It's a random walk on an undirected network where possibly we put some weights on the edges. So that's the reversible case. And I wanted to do one example of a non-reversible chain. That non-reversible in general is going to be much more difficult. Right? In the reversible case, it just really has a lot of really nice properties, both intuitively, because you can think about time running backwards and forwards, and practically that you can avoid matrix stuff a lot of times, things like that. Non-reversible, we can still think of it as random walk on a network with weights, except that we have arrows, maybe one-way arrows or two-way arrows, and you can have different weights in both directions. That extra generality makes it much, much, much harder, okay? So just want to do one example of a non-reversible chain. Non-reversible example. Okay, and that example is Google chain. More precisely, Google PageRank. Google PageRank, which was the algorithm that Google originally used and still is using some form of, is based exactly on a Markov chain, and it happens to be a non-reversible chain. And I wanted to tell you about what that chain is, how it's useful, where that came from. Okay, so this is just one example, but this is a very big, important example. Has anyone here heard of Google? Yeah. Well, okay. Well, if not, you can Google for it, and you'll find a lot of stuff there. It's a search engine, and it's all based on Markov chains. I basically want to explain how that works. So, well, you can kind of guess that what the chain is. The states are going to be web pages, right, and the links are going to be links, right? Hyperlinks, on that is, we have the entire World Wide Web, and some pages link to other pages, and that's going to form a Markov chain. We're going to look at the stationary distribution of that chain and see what we can say. It's not going to be reversible, so we can't just write down the stationary distribution as easily as there, but we can still talk about how could you try to compute that thing, especially considering how large the web is. Okay, so just for the sake of having a picture, let's assume that the World Wide Web only has 4 pages, which is an underestimate, but at least I can draw something conceptually. So there's only 4 pages on the web. I just made up a little example. So we have 4 web pages numbered 1 through 4, and as I said, we're going to draw arrows that just represent links. So just this example I made up. Page number 1 links to page number 3. That is, if you go to this web page, you see a link that takes you to this web page. Okay, page 1 links to page 2. Page 2 links back to page 1. Page 3 is not so nice. They don't link back to page 1. Page 2 links to page 3, and page 3 links only to page 4. Page 4 has no links on it, right? Not every web page links to other pages. It may just be that page. All right, so that's, I mean, okay, that's an oversimplification of the web, but this gives you something to think, if you understand conceptually really well what's going on with 4 pages, then, you can imagine in principle there could be billions of pages, and you're just imagining a gigantic version of, some very complicated link structure, but basically you just have web pages linking to each other, okay? And so I want to basically explain what this algorithm does. So to put it in context, I'll talk a little bit about the earlier history of search engines, Google was started in 1998 by Brin and Page, who were Stanford grad students, and they ended up dropping out to work full time on Google. The name is kind of convenient. Brin and Page. Larry Page, it's kind of convenient for him that Page is in the name PageRank, but it's also a pretty natural name, right? Because this is a way for ranking web pages. So the basic problem is, suppose you search for a certain thing you're interested in, okay, and there might be millions or even billions of pages on the web that contain that topic, right? So the fundamental question and the insight that that made Google way better than any of the other alternatives at that time. I mean, now you can debate whether they're still the best or not, but at the time it was a huge, way beyond any of their competitors in terms of the ranking, right? Because you don't have time to search through a million. If you're searching for chess and there's a million pages, you don't have time to go through all of them. The question is, which page should come up first, second, third? It's the ranking, right? So you look for all pages that match your query. What order should those be displayed in? Okay. So what the earlier websites took pretty crude, naive approaches to that question. For example, I mean, some of the earlier search engines were basically trying to be human curated, like a museum, right? You have someone who's like, recommends this page is really good, right? And they try. Obviously, that doesn't scale so well when the web has billions and billions of pages now. It doesn't scale so well. And then I don't know, so maybe what else could they have done, like alphabetical or something like, it's kind of useless. And some of the early search engines, the ordering was based on how many times the page used that word, right? So if I'm looking for chess, then a page that mentions chess 100 times must be like much better than a page that only mentions chess once. Okay, well, obviously that opens itself up to abuse, right? And you can just like list a dictionary on your site like repeated many times for one thing, but even if you're not trying to abuse the system, it's like just using the same word over and over again doesn't mean that that's the most reliable, insightful, useful page on that topic. Okay, so the earlier sites were not really using the network structure of the web at all. And possibly Alta Vista was one of the first search engines that actually at least tried to do something with the actual structure of the web. And so at some point it was realized that actually, right, this is, the World Wide Web is a network, and the structure of that network is valuable information for doing these rankings. Okay, so then they started basically saying that a page is important if a lot of other pages link to it, right? Which was a big improvement. The problems with that, well, first of all, it's very easy to abuse that, right? You can easily just create thousands of dummy pages linking to your page. But even aside from the abuse question, it's like, just because a certain page has a lot of other pages linking to it, that doesn't necessarily mean that it's that important if those pages that link to it are garbage, right? So the insight of PageRank was that the importance of a page should be based not just on how many other pages link to it, but how important those pages are, right? So that's the key idea. So we have to try to make that mathematical and then show how that relates to Markov chains. But just intuitively, the importance of a page, as we want to rank the more, we want to give each page a score for how important it is, right? And rank them in order of importance in this sense. Importance of page should be based not only on which pages linking to it, the number of pages, and the importance of each one. Well, that sounds like a circular definition. That we defined importance in terms of importance. But that's okay, actually, because that suggests an eigenvector equation, which we'll interpret as a Markov chain. So if we let SI, just think of S as standing for score. That is, we're going to give each web page a score. And let me just index it with J. So that's the score of the jth web page. And so Brin and Page said, I mean, they defined, they said, we want to give each page a score such that Sj equals the sum of Si Qij, and I'll tell you what Qij is, summed over all I. Qij, well, they pointed out basically, a simple thing to do would just be to let this score of the jth page be the sum of all the scores of all, summed over all I that link to J, right? So in other words, you're thinking of a link, an incoming link is like recommending that page, and add up all the scores of the recommenders, right? Except a problem with that is that some pages may only have like one outgoing link, and other pages may have 1,000 outgoing links, and it seems a little unfair to count those kind of as equal recommendations, right? So it's like imagine that a certain page has kind of a certain budget for how much stuff it can recommend, and so if it recommends 1,000 pages by having 1,000 links, then each of those should be diluted, right? So that's what this Qij is going to do. So we're going to let our matrix Q just be the matrix we would get if we think of this as a Markov chain, just for this example. If we think of a Markov chain where we're just randomly following links, right? So in this example I made up, from page 1, you can go to page 2 or page 3, assume equal probabilities. So we would do 0, 1/2, 1/2, 0. It goes to page 2 or page 3. From page 2, you can go to page 1 or to page 3. So from page 2, you can go to 1 or 3. So 1/2, 0, 1/2, 0. From page 3, you can only go to page 4. So that's just going to be 0, 0, 0, 1. Page 4 is kind of annoying, right? They don't recommend anything. They're just, they're their own thing. But we actually want to have a Markov chain here. So we assume that from page 4, you can go anywhere on the web with equal probability. So I'm going to just change this to 1/4, 1/4. That's like if it links to everything. Okay, so you define Q in this way, where you're just doing all the links, but you're making each row sum up to 1. And if there's a page that has no links, then just make it 1 over the number of pages on the entire in the entire web. So this has a pretty natural interpretation that you might call like that is what you imagine is you have. And this is what they were thinking about. That part of the motivation, I think, that helped them was you imagine someone, randomly surfing the web, right? So what do you do? Well, you're read a page for a while, and then you're done with that page. And if you're like really bored, you just start clicking random links, right? Click a random link. It's a lot of fun to do on Wikipedia, right? There was a good XKCD about that, right? Click a random link. You keep clicking random links, right? You're just randomly surfing the web. That's kind of a natural thing to think about. And then, now, what happens if you reach a page that has no links, but you're not ready to stop surfing the web yet, right? You don't give up in despair. Then the assumption is then you just open a new window and just go to some other random page, right? So then you can continue your random walk instead of being, you don't really want to be trapped on that page forever just because it doesn't have any links, right? So that's what this chain is doing. Okay, so then this equation should make some sense, right? It's just saying, the importance is based on the importance of the pages that link to it. Qij is 0 unless there's actually a link from I to j. So you're only adding up the terms where there actually is a link there, and then the Qij's may not all be equal because of this dilution thing. All right. So in matrix notation, that just says that S, which is S is the vector of all the page ranks, right? Is equal to S times Q. I.e., what does that say? That equation looks familiar, right? It says that S is the stationary distribution. S is the stationary distribution for this random web surfing chain. Random web surfing chain. Okay, so this has a natural interpretation in terms of stationary distributions as well. That is, intuitively, we think of the stationary distribution as giving the long-run probabilities of being in different states, right? Which says, I'll just clarify that if S is normalized. And of course, if you have any solution to this, just divide by a constant to make, as long as you have non-negative numbers here. So if S is normalized. So we just solve this matrix equation, right? This is some gigantic linear system of equations, right? That is, billions of pages, right? So if there are 10 billion web pages, then Q is going to be a 10 billion by 10 billion matrix. So this is an immensely difficult computational problem. But in principle, all you're doing is solving this linear system and then normalizing it. And then that's the stationary distribution by definition of stationary distribution. So in terms of the interpretation of stationary distribution as the long-run fraction of time of being in a certain state, what this is saying is that if you imagine just like randomly surfing the web for ages and ages and ages, and in the long run, what this says that the importance of a page is the long-run fraction of time that you spend at that page, right? So that's kind of intuitive, right? The pages that are more important, you'll find yourself spending more time there in the long run. So that's what it's doing. Okay, so you can interpret this as a Markov chain, as I just said, but you might object, well, really, this is just an eigenvalue, eigenvector thing. It's just a matrix equation, and do we really have to give it this probability interpretation and really interpret it as a Markov chain? And so I wanted to show you like something about why is that actually a useful way to think of it. One reason is what I just said, that intuitively it makes sense to think of these long-run fraction of time for randomly surfing the web. So this gives a nice extra interpretation to this. But I also want to show you how this helps with the computation, because the computation is immensely difficult. That if you try to solve, the usual method for solving a matrix equation is Gaussian elimination, right? You do all these row operations, right? 2 times row 1 plus row 3, and all, swap rows and multiply row, right? All that thing. The complexity of Gaussian elimination, if you have m linear equations in m variables, is of the order of m cubed. It's a cubic complexity. You may be happy that that's polynomial time, but in practice that is not so good. If m is like 10 billion, and if you have the order of take 10 billion, that's 10 to the 10, cube it as 10 to the 30. 10 to the 30, so you'd have of order 10 to the 30th operations to perform. You don't want to do that, even on a fast computer. So, okay, so I want to show you how Markov chains not only gives you a nice interpretation here, it actually helps with the computation, which is, as far as I know, how at least how Google was originally doing this, and I'm sure they've refined things, but in spirit, it should be similar. That's the basic principle. So to give this the full Markov chain interpretation, we want to, and connect this back with what we're doing. We want to say, is this irreducible? And, does this have a stationary? How do we know the stationary distribution exists? And how do we know that it converges to the stationary distribution and things like that? So actually, what Google uses or used in the original Brin and Page, while they were still grad students, wrote a paper with the idea for Google, and then they started actually the company. So the paper that they wrote actually gives the ideas, and what they said in that paper is they set up an equation like this, but then they said actually we're going to use another chain instead, which I'll call G for Google. So here's the actual Google chain. The Google chain is alpha times this one that we just did. It's mixing together two Markov chains. Alpha times Q. So Q is the matrix we just defined based on the web, plus 1 minus alpha times j over m, where m is the number of pages. So in other words, Q is an m by m matrix, and J is the matrix of all ones. So I want to explain why did they do this. And alpha is a number between 0 and 1, just a constant. So think of alpha as a probability, because it's a number between 0 and 1. So what this is saying is, imagine that you have this person randomly surfing the web, like we were saying. Now with probability alpha, so they flip a coin that has probability alpha of heads each time. If the coin lands heads, they just click a random link on the page that they were on, right? That is, they actually use the Q chain. But if the coin lands tails, they use this chain instead. Notice J over M is a valid Markov transition matrix, right? Because the row sums are 1 and it's all non-negative. So this is, so with probability alpha, just follow the link. With probability 1 minus alpha, we do what's called teleportation. Teleportation is just the fancy word for saying don't follow the link structure anymore. Now just go to a random, uniformly random page. So this term is the teleportation. All that means is with probability alpha, just follow the link structure. With probability 1 minus alpha, just open up a new window in your web browser and go to a completely random page at that point. Of course, alpha has to be chosen. In the original paper suggested alpha equals 0.85. Now, that's like Google's magic number, 0.85. And there's been a lot of speculation and discussion about why did they use 0.85. So it's saying, I don't know whether they still use 0.85, right? That was the original value they proposed. So 85% of the time, you're just following random links. 15% of the time, you're teleporting to random pages. The reason, not specifically for this 0.85, but the reason for adding this extra term is that this makes things really, well, one reason is it makes things really nice in terms of the theory that we developed for stationary distribution. For the actual web, if we just had this part, we don't know whether it's irreducible. Can you get from anywhere on the web to anywhere just by clicking links? Well, I guess if you have this page, that would help a lot. But it may take ages to get from one page to another. And this is kind of allowing there to be some small probability of getting from anywhere to anywhere in one step. So this guarantees irreducibility, for one thing. And we have the other result about, that sort of the nice case is when some power of the transition matrix has all entries positive. In this case, notice, this is extremely tiny, right? This is only, if alpha is 0.85, this is 0.15, m may be 10 billion. So you're adding some tiny number, but at least everything's positive. You don't have zeros anymore. So no zeros in transition matrix. G. So that has some advantages. And in particular, we know that all the results about, even though it's not a reversible chain because the arrows may be going in one direction for the web, the results that from last time that I stated that there exists a stationary distribution. It's unique. The chain will converge to it. All this nice stuff all applies. Okay, so we have this thing. Now, how do we actually compute, though? Right? Because since it's non-reversible, we can't just write down a simple equation and immediately write down the stationary distribution. A stationary distribution is something very, very complicated here. But on the other hand, if we go back to the definition and try to solve this matrix equation, then we're trying to do Gaussian elimination with 10 billion or 100 billion equations. It's not so good, right? So the idea that for computation is to use the fact that the chain converges to the stationary distribution. So you use convergence to stationary distribution, to stationarity, to actually to solve. We don't need to solve it exactly, right? All we really need is an approximate solution to this. Okay, so we know that if we run this defines a Markov chain, right? Either you follow the link structure or you teleport each time. Follow that, run that chain for a long time, it's going to converge to the stationary distribution no matter what the starting point was, right? Start with any distribution you want, right? Run the chain for a long, now, there are some very difficult mathematical and computational questions about how long should you run the chain for, and those are not really well understood for a chain as complicated as this. So in practice, what people do is just run it as long as they can, or run it until it looks like it has stabilized. And you don't know for sure that if you then ran it another week, it would change to something else. But if it looks like it's stabilized, then you just take that as your approximate solution. Okay, so how do we actually run this chain, though? The computation, I mean, it looks like it's going to be extremely, extremely difficult because of these matrices are so large. It's actually much simpler than it looks, and I just want to show you why. So let's let t be our initial probability vector. That is, if you want, t could just be 1 and then all zeros. That just says always start out at page 1, right? Or let t be 1 over m all the way through. That is start at a random page. We need some starting distribution to start out the chain. So that's the initial that is this. In other words, this is the PMF at time 0 written as a row vector. So initial probability vector. Okay. So we proved before that if we want the probability distribution after one step, all we have to do is multiply on the right by g, right? So t times g is going to be the distribution after one step, right? We did that before. And then if we want the distribution after 2 steps, we multiply this by g, so we would get tg squared, tg cubed, and so on, right? Okay, so let's just quickly see what does t times g actually look like. So t times g, I'm just going to multiply this by t. This is alpha tq plus 1 minus alpha tj over m. And actually, this is not so complicated. Because if you think about what Q looks like, Q, that's this, that's this chain that captures the link structure of the entire web, right? What do you think that matrix looks like intuitively? It's a lot of zeros. This is like 10 billion by 10 billion or 100 billion by 100 billion. But right, a typical page, might have, I don't know, 3 links or 10 links or even 100 links. You're not going to have many pages that have tens of thousands of links or millions of links, right? But this is a 10 billion by 10 billion. Okay, so this is dominated by zeros. So in other words, we would say it's very sparse. That is sparse, meaning mostly zeros. Now, Google has a lot of, very, very, very good computer scientists working on some of the, data storage computational issues of how do you actually, what data structure would you use to store this matrix and keep track of where all the zeros are, right? In other words, how do you efficiently keep track of where the zeros are and where the non-zero terms are? Because it's mostly zeros, okay? But at least intuitively, this matrix has so many zeros in it. And having a lot of zeros makes it a lot easier to do matrix multiplication, right? You do need to be clever in keeping track of where the zeros are, but it helps a lot with doing this multiplication. Now let's look at this other term. Let's think about t times j. So remember, t is just some vector of probabilities that add up to 1, right? And then J is a very simple matrix. J is just all 1s. So I'm going to take this vector t, and I'm going to multiply by j, and then just matrix multiplication. T is a row vector, so you're going like row, dot it with a column. But you do a dot product with all 1s, that just says add up the entries of t. Well, if you add up the entries of t, you get 1, right? Because t is a probability vector. So t times j is just all 1s. Because you're just going, t, add up, right? Add up the elements of t. T elements add up to 1. That's very easy, just all 1s. Divide by m. So that term is easy, okay? So actually, this is not as bad as it looks. Now that we have t times g, we use that as the new t, right? That is, this is after running it for one step. And so then we do tg squared. That is, we do tg times g, which is tg squared. Well, we do that in the same way. That is, tg is now playing the role of t. And we multiply this by g, and that's not difficult to do for the same reason I just said. So then we have tg squared, tg cubed, and so on. Run this for a very long time. That is tg to some large power. That corresponds to running this chain for a large number of steps, right? So then in the limit, if you do tg to the n, meaning you ran it for n steps, and you let n go to infinity, that's going to converge to the stationary distribution. The stationary distribution is the page rank vector. So then you have page rank. Okay, so that's actually computationally a lot easier to do. Just run this chain in this way, rather than trying to solve the 10 billion by 10 billion matrix system. And it has this nice interpretation in terms of randomly clicking links and randomly teleporting every now and then. All right, so that's the essence of Google PageRank, and that's the end of Markov chains. So I'll see you on Friday.